Welcome to homework.
So in this case, we have a bar. Let me actually kind of draw a little schematic over here so that we can kind of reference it. And it's pivoted here. So it's kind of like an inverted T can swing here. So this one is quite a bit more difficult than the previous one. Partly because when you have pendulum and when you're doing energy, you have to be a little careful. So what I can do is I can look at we have no springs in here, so we have no elastic potential energy, but we do have gravitational potential energy because this thing is swinging back and forth. And in fact, it's gravity that's providing the restoring force to bring this system back to its equilibrium if it's perturbed. So what we can do is, if we look at the potential energy of this piece, and then this piece individually. So for this piece, if we measure the datum from here, the potential energy is L over 2, where this length is L, M1G, and this is the mass of this, M1 is the mass of this bar here. And so then we have 1 minus cosine theta. Okay, so if we perturb this and move it over here, the center of mass of this bar has risen up 1 minus cosine theta. Now for this piece here, the center of mass is down here, and so we can see that it rises up L1 minus cosine theta. So our potential energy for this bar is M2GL1 minus cosine theta. Now, we can leave it like that, but we're told that we have small oscillations. So we can assume that theta is small. But when we're doing energy, we got to make sure we keep up to the squared term of our energy. And you'll see why that is in a second. So the first approximation to cosine of theta is simply 1, which means that this is 0 and this is 0, meaning that we have no gravitational potential energy in our system dropped out, which is going to tell us is not going to say anything about this thing being able to oscillate. Now, however, remember cosine of theta, the Taylor series approximation is 1 minus 1/2 theta squared. So if we take keep up to the squared term, then this just becomes 1/2 theta squared, and likewise this. So we can plug that in, and then we get our potential energy where it's not trivially 0. It basically it's a quadratic function of theta. And that's what we want if we want a linear function in the end, because we're going to take a derivative of this. Now, the kinetic energy, we have the kinetic energy of this bar and then this bar, and those are about this bar about this point here is 1/2, 1/3 M1L squared theta dot squared. And this one, using the parallel axis theorem, we have about its center of mass is 1/12 M2D squared. M2, yeah, well, what did I, yeah, okay, yeah, D I said was this length here, right? And then the parallel axis theorem, we get M2L squared to shift it up to here, since this is the distance L. So this is the kinetic energy in this bar. Now, what I did is I could just say, okay, when we add these things together, we can define what I call an equivalent mass and an equivalent stiffness. And so we were given the linear density of these bars, so that's what I call rho here. So the mass of this bar is rho L, and the mass of this one is rho D. So if we look at our kinetic energy terms, and we can lump them into a group like this, 1/2 some equivalent mass times theta dot squared, we can see that one part of the equivalent mass is this, which turns into this term, and the other part is this, which becomes this term. And likewise, we can take our potential energy terms and say they're 1/2 some equivalent stiffness times theta squared. And so we can see that the one term is this, which is here, and then the other term is this, which is here. Now, we know that this thing, so these are constants, the coefficients, these are functions of time. We know that this thing is conserved, so we take the time derivative, and we simply get that the time derivative is this equivalent mass, theta dot times theta double dot, plus the equivalent stiffness times theta dot, and that equals 0. And again, this is true for all time, so we can divide through by the theta dot, and we get MEQ theta double dot plus KEQ theta equals 0. And these, we can then go on, and let's see here, they wanted us to calculate the natural period of vibration. Okay, so omega n squared is KEQ over MEQ. So we can plug those values in. Here's KEQ, MEQ. We can, and I've rewritten them here for reference. And we can see that there's a rho that drops out because the linear density of each bar was the same. We can then rewrite things, and if we note that in this case D equals L, then lots of stuff cancels out. Okay, so we cancel out lots of stuff here, and we wind up with the simple expression of just 18 times G divided by 17 times L. And L happens in this case to be 2 feet. And if we use G as 32.2 feet per second squared, we get that the natural frequency squared is 17.0 radians squared per second squared. And the natural period is 2 pi over the natural frequency, and that turns out to be 1.52 seconds. So it's interesting. Really, all we needed in here was for values for L. That's all we needed. We didn't need rho because it canceled out. And shouldn't be surprised because rho acts essentially like a mass, and when you have a pendulum, the mass cancels out. So we shouldn't be surprised that that cancels out, and we actually didn't need that value. And then just because D and L are the same, things get very simplified quite a bit.